Okay, so long time no see. So here is the situation, which is quite critical. We are already on slide 57 of my 4-hour lectures. I have almost no voice left, so I have no backup plan. So please interrupt me if you have any question. Okay. Now let's talk about a different notion of weakness, which is a preservation of hyperimmunity. So let's first make a few definitions. A function from the integers to the integers, g dominates f if eventually it dominates. So if eventually it is pointwise greater than f. And a function is a modulus of a set if every function dominating f computes the set. And a function is hyperimmune if it's not dominated by any computable function. And last, an infinite set is hyperimmune if there is no infinite computable sequence of pairwise disjoint blocks intersecting A. So it's a very strong sense of immunity in the sense that you cannot even approximate an infinite subset of it by blocks. And there exists a duality between computational power, so computing sets, and the ability to compute fast-growing functions. So for example, the sets admitting a modulus are exactly, so have been characterized, they are exactly the hyperarithmetic set, the delta 1,1 set also. Or the sets of high degrees by Martin's domination theorem, so the sets so that the degree of its jump computes zero double, are exactly those which compute a function which dominates every computable function. And this is where I said that dominating was eventually dominating. It's because here I just want to say that function dominates every computable function. And then there is this duality between being hyperimmune as a set, so you cannot approximate infinite subset of your set even by blocks, and the ability to compute functions which are not dominated by any computable function, so hyperimmune functions. And this is the last group which is of interest for us. So fast-growing functions or even hyperimmune functions are related to genericity in the following sense, for cohen-genericity. So a set of integers is weakly one-generic if for every CE dense set of strings, you you intersect it. So it just means that you are cohen-generic for all the CE dense set of strings. And first, it's easy to see that every weakly one-generic set is hyperimmune as a set. Why? Because if you have a computable sequence of pairwise disjoint blocks, then for every string you can find an extension so that it will have many zeros, and so that the intersection of one of the blocks with this initial segment will be the empty set. You could also define it in terms of function domination. So for every computable let's just keep it that way. So if you are pairwise disjoint blocks, there are blocks so that the minimum is arbitrarily large. And so given a string, you find a block which is so that the minimum of the block is bigger than the index of sigma, and you add many zeros, and this is an extension which forces the block to have an intersection with sigma. Okay? The other direction is very interesting. Every hyperimmune function computes a weakly one-generic set. So let's just elaborate a little bit on that, because I have so much time. So assume you have a collection of sets. So you have W0, W1, and so on. These, let's interpret them as a CE set of strings. But you don't know which ones are dense. So if you want to build one generic, so if you want to build an infinite set which will intersect all the dense sets, what you can do is you get sigma 0, so you start with the empty string, and then you add elements, and hopefully at some point W0 will output an extension of your string. But maybe it will be too late. Maybe we'd say, hey, here I was able to extend this initial segment, but it's something incomparable with what you have defined so far. Too bad. Let's continue. Let's assume it was still not dense, it was just a guess. Let's continue. And later, maybe this one will still tell you, oh, but I was able to extend this initial segment. But now it's too late. You were continuing. And at some point, you can say, okay, you fooled me once, you fooled me twice. So let's wait. And I wait until you output something which will extend me. And no luck. It was precisely the point that had no extension to satisfy. So what you can do is, if you have a fast-growing function, let's assume that W0 is dense. It means that for every length L, you can associate a minimum time T such that for every sigma of length L, there exists some tau in W0 enumerated on time T, so that tau extends sigma. So you can look at this map. This map is computable, assuming that it's total computable, assuming that W0 is dense. So because it's total computable, if you have a function which is hyperimmune, this is a function which infinitely often actually will be bigger than this map. Okay? So what you can do is start making your sequence, but at each step, what you do is, okay, you want to decide whether you will add an element or not. So what you do is you enumerate W0 on time f of the length of what you have built so far. So here, let's say L, f of L. If you find an extension, you take it. And if you don't, then you just add an element and you, again, so at each step, each time you add an element, you interrogate the, thanks to this function f, you ask whether you can find an extension. And because your hyperimmune function is growing, so it's not dominated by this, it means that at some point, this will be large enough so that you will wait long enough to find an extension on time. Okay? And if W0 is not dense, well, you can ask the question, and maybe it will wait long enough to find an extension. Maybe it will not wait long enough, but who cares, because it's not dense, so you have nothing to do. So to satisfy only one requirement, one CE set is easy. You have to be a little bit more careful if you want to satisfy infinitely many requirements. Because when you find your extension, you are going to make a jump in the length. But maybe in this intermediary length, the function f was going to be large enough to witness some extension of some other requirements. So you have to be, I'm not going to go too much into the details, just to you have to be a bit careful about when you take an extension, you are jumping some intermediate stages, and so you still have to interrogate the f on all these intermediary lengths to be sure that you are not missing someone. And so you have to put priorities between the W's. Okay? So it's a well-known theorem, and you can find a proof in any textbook on computability theory. So here I define it just for one requirement, and I'm cheating because we have this issue of intermediary steps. Anyway, so we can define a preservation of hyperimmunity as following. So a problem admits preservation of hyperimmunity if for every set z and every z hyperimmune function, so by z hyperimmune I mean that the function f is not dominated by any z computable function. For every weak instance, so every instance of P which is z computable, there exists a solution so that f is still hyperimmune relative to the join of the solution and z. Okay, so you preserve. You can add solutions, but your function still remains hyperimmune. So preservation of z hyperimmunity can be also expressed as a scheme of preservations in the standard framework, in the sense that you preserve wf for every function f. So this is a collection of all z so that f is z hyperimmune. And of course, if f is not hyperimmune, then this wf is the empty set, but it's vacuously true. But so the interesting cases are when f are hyperimmune. So let's just look at co-enforcing, because it's always our baby example is with co-enforcing. So it's still with strings. You take the extensions as refinement of conditions, and the denotation is the collection of candidates are the ones which have this sigma as initial segment. We can show that if you are sufficiently generic for every hypermuon function f, so for every function f, which is hypermuon, for every sufficiently generic coin for G, f is still G hypermuon, and it relativises well. So we want to show the following density lemma. You have fixed a hypermuon function f, and you have a Turing functional phi e. And what you want to show is that the following set of the condition which forces either phi e of G to be partial or not to dominate f is dense. So if you satisfy this, so if you intersect this for all the set D's, then you will not G computably dominate f, which means that f will be computably dominate will be G hypermuon. Okay. So let's try to prove this lemma. We have again a three-case analysis. So given a condition, define the partial computable function. So given a condition and an input x, try to find the least y, if it exists, so that you can find an extension. There exists an extension for which you halt and you are equal to y. Okay. So this defines a partial computable function. It might not be total. So first case, there is some x for which is defined and for which you are strictly smaller. Then it means that there exists an extension for which you will halt on a small value. So you are forced not to dominate f as witnessed by x. Okay, so you have an extension which forces this. In second case, you are not total, which means that there is some input x, so that whatever the extension, you will not find any y for which you halt are equal to y. This means that actually sigma already forces phi e to be partial as witnessed by x. Okay. And last, if you are the negation of case 2, then it means that your function is total, h. And if you have negation of case 1, it means that each time that it dominates f. So you have a total computable function which dominates f and which contradicts the fact that f is hypermuon. So it's always the same kind of structure, saying either you can force some sigma 01 events, some wrong sigma 01 events, or you can force some pi 01 events, or you can approximate an object that you should not be able to approximate. Always the same kind of structure. Okay. So let's directly go into the general abstract theorem. We say that for a family of formulas, gamma, a forcing question is gamma compact if for every condition P and every gamma formula, phi of Gx, if it answers yes for the question exists X so that phi of Gx, then you can find a finite set of candidates F of integers so that actually it will say yes, there is X in F so that phi of Gx. Means that you are able to bound. Actually, I could replace X by a bound Y. I say exists X smaller than Y so that it holds. It would be the same. So you are compact if you find an existential formula in the right part of your question, then you can bound this existential. And so suppose that your formula, you have a notion of forcing with a forcing question which is sigma 01 preserving and sigma 01 compact. Then I claim that the density lemma for preserving hypermunity is dense. So this is still the same formula, saying either I force partiality or I force not to dominate the function. And so abstractly, let's define, so given a condition P, let's define the partial computable function, which on input X will search for a finite set F so that it answers yes to the question, is there some Y in F so that phi eg of X halts and is equal to Y? We have, and you output a 1 plus the max of it so that you have strict inequalities, so it's just technical detail. So we have three cases. First case is either the answer is yes for, so either you find such an F and with small values, so the max of F are, all the sets, the elements in F are small, then you can find an extension which forces to halt and to output a value which is smaller than max of F and so be smaller than F of X. So you are done. Or, and this is where you use compactness, there exists some x, so the function h is partial, which means that there is some x, so that we cannot find any finite set f for which it answers yes. But by sigma 01 compactness, it means that actually the function will also answer no to the question, is there some y so that phi of x has is equal to y? Which means that we can find an extension which will force partiality on input x. And last case is still the same. If you fail case 2, it means that you are total. If you face case 1, it means that you dominate f, and so you contradict the fact that f is hypermuon. Yes? 3? No, I don't assume that. Yes. And actually, preservation of cone avoidance, so cone avoidance is equivalent to preservation of hypermunity. For every pi12 problem, so even if it's not pi12 actually, for every problem, if you admit cone avoidance, you admit preservation of hypermunity. But this works only in the relativized form. So saying for every z, for every c which is not z computable, and so on. So if you work with an unrelativized version of cone avoidance, an unrelativized version of preservation of hyperunity, these do not coincide. We can also show that if you admit cone avoidance, so if you avoid one cone, you can actually avoid omega cones simultaneously. So you have a countable sequence of cones which are not computable. For every instance, you can find a solution so that all these cones will still not be computable simultaneously by your solution. But it's not equivalent to preserve one hypermunity or to preserve omega hypermunity simultaneously. And actually, you have a strict hierarchy. So you have theorems which admit preservation of k hypermunities, but not k plus 1 simultaneously. So this is beyond the scope of this tutorial, but it's a general phenomenon in computability theory that a lot of weird behavior can happen. But as soon as you impose some kind of naturality condition, then things start to have a nice shape. And by naturality, often it's with relativization properties. So there was the notion of over a cone from Antonio Montalban, and here is if you ask a good relativizable notion of cone avoidance or relativizable notion of hypermunity, then this coincides. So what we know still so far about the forcing question is, so if you are sigma 01 preserving, you admit cone avoidance. If you are sigma 01 preserving and sigma 01 compact, then you admit preservation of hypermunity. Actually, so because they coincide, I don't know whether whether we can show that as soon as you have a sigma 01 preserving forcing question, you can find a sigma 01 compact forcing question. That's something, it has not been well studied at all. So these are questions that we can wonder. Let's talk about another weakness property, which is compactness avoidance. I mean, it's a family of weakness properties. And so cone avoidance was justified by trying to separate problems from AC0. Now we are going to want to separate problems from weak Koenig's lemma. So weak Koenig's lemma, let's recall that it means that for every infinite binary tree, you have an infinite path through it. And so weak Koenig's lemma is part of the big five, and it's equivalent to basically to compactness arguments. So it's equivalent to the Heine-Borel cover lemma, or to Gödel's completeness theorem, and so to many theorems. And so what is interesting is a characterization using the notion of diagonal non-computable functions. So a function is diagonally non-computable, or simply D and C, if for every E, f of E is different from phi of E. So by definition, it's why it's called diagonally non-computable. By definition, such an f cannot be computable because it diagonalizes against every Turing functional. And let's just mention that f has to output a value. For it's a total function. Even if phi of E is not defined, then it can be anything. And if it's defined, it has to be something different. Then there exists a computable infinite binary tree, so an instance of weak Koenig's lemma, computable instance of weak Koenig's lemma, so that the set of solutions, the class of solutions are exactly the 0, 1 valued DNC functions. So you can construct a tree which captures so that the infinite path captures exactly the 0, 1 valued DNC function. So here is the definition of this tree. It means that sigma, it's the set of sigma, so that so far from every smaller e, when you execute in at most the length of sigma, you still witness that you are. So either this did not halt or this is a difference. Okay. And conversely, for every computable infinite binary tree, every 0, 1 valued DNC function computes an infinite path through it. So which means that this tree is maximally complicated to solve. There is one universal instance somehow. So the idea is very simple. Given a node that we know, so given let's just start with the empty node, the roots. We want to know whether we want to go on the right or on the left. But the difficulty is that we don't know which node is extendable or not, extensible into an infinite branch. We want to pick an infinite sub-branch. So what we can do is to define a program which will explore both the branches, so on the left side and on the right side. And if one of the two sides happens to, if one of the two branches happens to be finite, then it halts. It knows it after a finite amount of time. It halts and outputs the side. If both happen to be finite, then whatever is discovered to be finite first will halt and output the side. Okay. But if we assume that actually sigma is infinite, if the branch under sigma is infinite, then at most, so it will halt on, so there is at most one of the two sides which will be finite. Then, if sigma is extensible, then if you call f of E sigma, it has to output a side for which you are infinite. And so you have now an algorithm to compute one more step to increase your initial segments with one more bit of information. So you can iterate. It's uniform. So the power of computing an infinite tree under a computable infinite binary tree, an infinite path through an infinite computable binary tree, is exactly the power of computing a 0, 1 valued DNC function. And we are going to use this characterization. So let's use still our toy example, so coenforcing. And let's show that if you are sufficiently coengeneric, then you do not compute any 0, 1 valued DNC function. So for this, we are going to prove the following density lemma, which says, so given for every 0, 1 valued Turing functional, we want to show that the following set is dense, set of conditions which force either to be partial or to halt on a value which happens to be equal to phi x of x. So to halt on a wrong value, not be a DNC function. So there are two ways not to be a DNC function, 0, 1 value DNC function. Either you are partial or you halt and you are equal to phi x of x. Okay? Still, three cases. So given a condition, define the following sigma 0, 1 set, which is a set of pairs xv, so that is there some tau which extends sigma for which I can halt on input x and output v. You will have recognized, of course, the sigma 0, 1 preserving forcing question of coenforcing. First case, there exists an input for which you halt on the wrong, for which you are able to halt on a wrong value. So there is some x so that the pair x and phi x of x belongs to W for some x so that you halt. Then you take the tau which witnesses the fact that you belong to it, and it forces not to be a DNC function. In the second case, there are two pairs, so x0 and x1, which do not belong to W for some x. Then I claim that I force, assuming that I'm 0, 1 valued functional, I claim that sigma already forces to be partial on input x. Why? Because whatever the extension tau, because neither x0 and x1 belong to W, it means that whatever the tau we take, you will never halt and be equal to either 0 or 1. But because you are 0, 1 valued functional, it means that whatever the extension, you will not halt. So sigma already forces the divergence. And in third case, then you are sigma 01 graph of a DNC function, which is not possible because no DNC function is computable. Okay? So what we exploited here is, so the difference between code avoidance here is that we had two different pairs, and we exploited the fact that we forced the conjunction of the two negative facts simultaneously. So this motivates the definition of pi-01 merging forcing question. The forcing question is pi-01 merging if for every condition and every pair of sigma 01 formulas, phi and psi, if the equation says no for phi and no for psi, then there exists a single extension Q which simultaneously forces the negation of the two formulas. So, which means that if you ask independently the questions, you can find a simultaneous, a compatible answer, a negative answer for the two of them. And so suppose that you have a forcing question which is sigma 01 preserving, so you always want sigma 01 preserving, and which is pi 01 merging, then you are able to force the density lemma for the one value DNC function. So this is exactly the same proof as before. Here is just that you have two questions, and you because you are merging, you can find an extension which forces the simultaneous answer. So let's just stop and look back at this picture. We had Jokushor forcing, which was on one extreme, saying if I do not already force my sigma 1 formula, then I answer no. And Cohen forcing was saying, if there is any way to force my sigma 01 formula, then I say yes, otherwise I already force the pi 01 formula. But if you are on this extreme end, it means that if the answer is no for one question and for another question, it means that you already force the negation of the first and of the answer of the other. So it means that actually you force simultaneously, you are pi 01 merging if you are on this extreme end. So what we exploited of Cohen forcing is the fact that it was extremal on this side. But Jokushor forcing is on this side and it's not pi 01 merging. Let's take a non-trivial example, which is not an extreme outside, but we still will not compute an E01 valued DNC function. Let's consider Soloway forcing. So Soloway forcing, the partial order, is a collection of closed classes of positive measure for the standard Lebesgue measure, okay, in the control space. And you are ordered by inclusion. So the denotation is C itself. Denotation of a closed class is itself. You want to compute a member of a closed class. For every sufficiently Soloway generic G, so if you are sufficiently generic, actually you will have a singleton element at the end, and so it's G. G computes no 01 valued DNC function. So you want to show the following density lemma. And for this, we are going to use what is called Lebesgue density lemma, saying that if you have a closed class of positive measure, then for every epsilon, you can find an initial segment so that the cone in it, so your closed class intersected to the cone, will have arbitrarily large measure within the cone. So it means that if you have a subtree of positive measure, you will find a node so that this tree will look very bushy, the sub-branch will look very bushy somehow. Okay? So let's try to prove our density lemma. You have a closed class, which is a condition, a closed class with positive measure. And let's take a sigma, which witnesses the Lebesgue density lemma. So that's locally, it looks like it has measure 0.9. Okay, so we find we zoom in and we find some place where it looks like it's almost have a measure 1. So it has measure 0.9 locally. Now you look at the following sigma 01 set. The set of pairs xv, so that the measure of oracle z, so that sigma followed by z, so you concatenate sigma and this infinite sequence z. On input x hat and equals to v, so the measure of those z is smaller than 0.2. So we have three cases. In the first case, so x and phi x of x, the pair belongs to W. Then you can find some tau so that P intersection to the cone below tau is positive. So because it has positive measure and because it has measure 0.2, you can find a cone so that you have positive measure and you hat. And so this is again a closed class because this is a Klopen, and you intersect a closed set and a Klopen. And this is an extension which will forcing to hat on a wrong value. Are you clear why we are able to pick such a tau? Okay. In the case 2, it means that there exists some x so that the pair x0 and x1 do not belong to W. Then I claim that if I take P restricted to the cone for which it looks like it has a big measure, and I look at all the y so that I diverge, then I claim that this has positive measure. Why? Because x0 does not belong to this, it means that the measure of the oracles of the form sigma z so that I hat is smaller than 0.2, and same for input 1. And so if you take the union of the two, it will have a small measure, and so it will force this. I'm going a bit fast, but so it's basic measure theory. And in the last case, then still abstractly, because this set is sigma 01, because if you asking for a sufficient measure to hat and output something is sigma 01 fact, then you have a sigma 01 graph of the density function, and so you get a contradiction. So this is an example for which if you answer yes or if you answer no, you have to find an extension. So you are not an extremal situation. The forcing question induced by that, which is this forcing question, is non-trivial. Let's talk a little bit more about diagonal non-computability, about DNC function. So it's not part of the big five. I'm not talking anymore about 0-1 valued DNC function. I'm talking about DNC functions, so which can output any value. And it's not part of the big five, but it's a very robust notion in computability theory. So the natural definition is, as a statement in reverse math, we can say for every set x, there exists a DNC function relative to x, that is, a function f, so that f of e is different from phi of e with oracle x. So that's the definition of DNC. And there are many equivalent definitions saying that you have a fixed point free function, so a function which will take a code of an XCE set and will transform into another code which yields a different XCE set. And it's equivalent to say that you can compute a function which will have high Kolmogorov complexity. It's equivalent to say that you are able to compute an infinite subset of an X random set for whatever it means in algorithmic randomness, and so on. C of x is Kolmogorov complexity relative to for x computable oracle. It's plain Kolmogorov complexity. So contrary to 0-1 valued DNC function, there exists a probabilistic algorithm to compute the DNC function if you are not just 0-1 valued. Just pick, so to find f of 0, just pick an element at random between 0 and 4. And for f of 1, pick an element at random between 0 and 2 to the 3, and f of 2, 2 to the 4, and so on. What are the probability to have an error? Here, there is at most one wrong value in this interval for f of 0. So the probability of having an error for f of 0 is smaller than 2 to the minus 2. And for f of 1, you have at most one wrong value among in this interval. So the probability of having an error is at most 2 to the minus 3, and so on. And so if you look at the global probability of having an error, it's dominated by the sum, by the series of 2 to the minus n minus 2, so 0.5. And by making larger intervals, you can make this probability of error be arbitrarily small, and so you can make arbitrarily large probability of success. So at random, there is a very simple algorithm for computing a density function. Let's still take coenforcing. Let's not compute density function. So not anymore 0, 1 value density function, but density function. So the look of the diagonalization lemma is very similar to what we saw. It's just that we are not anymore considering 0, 1 valued Turing functionals. Look at arbitrary Turing functionals. We want to either to force to be partial or to halt on a value and be equal to phi of 6. So, given a condition, a Cohen condition sigma, define the following sigma the one set, which is exactly the same sigma the one set, except that here V is not anymore 0, 1 valued. Okay? And we have three cases. Either there exists an X, so a wrong value for which you halt, then you take the tau which witnesses it, and still you have your diagonalization. Always the same. I'm voluntarily redundant to see that it's always the same idea, always the same scheme. In case 2, this is where it changes. In case 2, there exists an X so that whatever Y, and it's not anymore Y to be equal to 0, 1, but for every Y, the pair XY does not belong to W. Then it means that whatever the extension tau, you will never find any value for which you halt equal to this value. So which means that sigma already forces to be partial. And in the last case, it cannot happen because you are sigma the one graph of a density function. So it's almost the same, except that here you have to force countably many pi01 facts simultaneously. But it's not an issue for coenforcing, because since it's extremal, if it answers negatively a question, then it already forces it. So if it answers negatively countably many questions, it will already force it will be already compatible for everything. Okay? But in general, we can define a forcing question to be countably pi0 n merging. It's the same as pi0 n merging, except that instead of having a pair of formulas for which it says no and you want to find a common witness of failure, of negation, here you have a countable sequence of sigma 0 n formulas so that you say no for each of these formulas. Then you want to find a single extension which witnesses the negation of all these formulas. Okay? And it's easy to show that if you are sigma 0 1 preserving and countably pi 0 1 merging, then you are able to force the density, to prove the density lemma. And so which means that if you are any notion of forcing, you will not, your generic set will not compute any density function. So what we know, more things. So we have learned that if you are sigma 0 1 preserving and pi 0 1 merging, so pi 0 1 merging, it just means 2 pi 0 1 merging, you have PA avoidance. So PA avoidance, okay, it just means 0, 1 valued density avoidance. So you are able to avoid computing a path through an infinite binary tree. And if you are sigma 0 1 merging and omega pi 0 1 merging, you have DNC avoidance. By DNC avoidance, so you can make a model of your problem, which is not a model of DNC, so which does not contain any DNC function. Okay. So it's still the common scheme is to understand the computational weakness of a notion of forcing. Just look at the shape and the combinatorial properties of forcing questions. And given that, it already determines a lot in terms of computability theoretic properties. So I still have 20 minutes. So I'm switching to my next lecture, conservation theorems. And so far, we manipulated only omega models. But the analysis in terms of shape of the forcing question is also useful for proving conservation theorem. So let's go back to the induction scheme. So recall we have two big families of schemes in weak arithmetics. You have many of them, but two big ones. The induction scheme, which says that if you hold for 0 and you hold If you hold for X, you hold for the successor, then you hold for everything. And you have a collection scheme. It says given some A, if for all X smaller than A, you can find a Y so that something holds, then you can find a uniform bound B so that for all X smaller than A, there is a Y smaller than B so that it holds. And if you look if you do not restrict these schemes, actually, these are equivalent. But if you are a bit more careful, it's interleaved. So the induction scheme for sigma 0, so for sigma 0 n formulas implies the collection scheme for sigma 0 n formulas, and collection scheme for sigma 0 n implies induction scheme for sigma 0 n minus 1, modulo some very basic base theory. So let's just look at the strengths of these problems. So you can consider the strengths of the various these schemes, so induction scheme and collection scheme. You have the induction scheme for delta 0, 1. So let's recall that the induction scheme is equivalent to the bounded comprehension scheme, which means that it says that the initial segments of your set belong to a model. So here, morally, it says that every finite combinable set belongs to your model. This is equivalent to the bounded comprehension scheme for sigma 0, 1 sets. Then you have sigma 0, 1. So sigma 0 n, induction scheme for sigma 0 n is equivalent to induction scheme for pi 0 n, so it collapses. While for a collection scheme, sigma 0 n plus 1 is equivalent to pi 0 n because of some quantifier collapsing here. That's just some tricky stuff. In terms of, you can also calibrate the strengths of these schemes in terms of regularity. Regularity says, basically it's just the bounded comprehension scheme. So I delta 0, 1 says that delta 0, 1 initial segments of sets, initial segments of delta 0, 1 sets belong to the model. I sigma 1 says that initial segments of sigma 0, 1 sets belong to the model, and so on. I could make my talk longer by going at very high levels of the hierarchy, but so any case, and it's also equivalent to the List principle at various levels. It has a more direct correspondence with the induction. So induction and List principle are easily proven to be equivalent. Collection is a bit more tricky. So the strength of RC0 is at this level. It's sigma 0, 1. Oh, no more battery. I used too much of pointer. So this level is the level of RC0. So basically, so you have Robinson arithmetic, the comprehension scheme, and the induction scheme for sigma 0, 1 formulas. Analog pointer, which is like the keyboard, isn't it? I can use the keyboard and my finger. And there exists, so there are various systems which correspond to these various strengths of induction. So for example, so at the second level, you have RC0, which is correspond to I sigma 1. At the lower level, there is another system, which is RC0 star, which corresponds to I delta 1 plus the exponential. The exponential just says that the totality of the exponential, so just says the totality of the exponential. And so there exists an easy way to see the first order part of these systems. You just remove the zeros on the top of your scheme, and this gives you the first order part of your system. So which means that the first order part of RC0, which means the set of its first order consequence, is axiomatized by Robinson arithmetic and the induction scheme for sigma 0, 1 formulas for which you have no set parameter. Okay. So given a family of formulas, we are often interested in, so given a theory, what we want to know is what is the set of its first order consequences. And a way of knowing it is through conservativity. So the theory T1 is gamma conservative over T0, where gamma is a family of formulas. If every gamma sentence which is probable in T1 is already probable over T0. And so one way of understanding the first order part of a theory T1 is showing that it's pi11 conservative. It's a pi11 conservative extension of T0, where the first order part of T0 is already known. And so if T1 is pi11 conservative extension of T0, then they have the same first order part, because every arithmetic formula is pi11. So given let's make a little bit of definitions. A second order structure, so which is parameterized. So now we don't work anymore with omega models. So a second order structure, so n is an omega extension of m if they have the same set of integers, and the second order part is bigger. So it can be misleading. Being an omega extension has nothing to do with being an omega model. Omega just means that you don't change the first order part. And by first order part, I mean in the sense of the structure, not in the sense of first order consequences. We can show that if every countable model of T0 admits an omega extension, into a theory of T1, into a model of T1, then T1 is pi11 conservative over T0. So it's the most basic way of showing that you are pi11 conservative. And the proof is very simple. So assuming, of course, that T0 and T1 are countable, so that we can use the Lowness theorem. So suppose that T0 does not prove pi11 formula. So the form for all x, second order quantifier, followed by an arithmetic formula. So let M be a countable model, because T0 is a countable theory. Let M be a countable model of T0 and the negation of the formula. So exists x and negation of phi of x. Now, if you take this model and take an extension, an omega extension of this into a model of T1, then it will also satisfy exist x negation of phi of x, because it will also contain x. And the arithmetic formula will not be, its truth value will not be changed, because we keep the same set of integers. So which means that n will be a model of T1 and of the negation of the formula, which means that T1 does not prove for all x phi of x. Okay, so far so good? So that's a very easy way of proving omega extension. So given, let's just check that time. So given a model of second order arithmetics, so we are just going to make a little definition. M square bracket G. This is the smallest omega extension containing M, G, and all the delta 01 definable sets over this extended structure. And it's so that actually M bracket G will satisfy the delta 01 comprehension axiom. So in the case where your theory T1 or T0 is a pi12 problem, then we can have a bit more precise construction, a more precise way of applying this theorem. So assume that for every countable model of T and every x and every instance of your problem in your model, you can find a solution so that the extended model will satisfy that you are a solution. Then you are pi11, so your theory plus P will be pi11 conservative over your theory. So the idea is just to start with M, and you take an instance and you find a solution so that it will again be a model of T plus say that I'm a solution to your instance, and you increase your model, and at the end you take the union of all of this, and it will be a model of T and of P. Let's just try to be a bit more applicated and work with a weak Koenig's lemma. Let's just show that a weak Koenig's lemma is pi11 conservative over RCA0. So this is a theorem from Harrington saying that if you are a countable model of RCA0, and if you have an infinite binary tree, then you can find a path so that if you add this path to your structure, then this is a model of RCA0 again. And so if you have this, you can iterate and make, given a model of RCA0, you can make an omega extension, which will be a model of weak Koenig's lemma. And so you have that weak Koenig's lemma is pi11 conservative over over RC naught. So here, it's basically the same notion of forcing as usual, except that will be a bit formal. So P is the set of infinite binary trees which are in the second order part of your model, of your structure. And you still have your forcing question, which says, is there some level in the tree so that for every node at this level, you satisfy your formula? This is the standard forcing question. It is still sigma 01. Then we can easily see that this is a forcing question, in the sense that if you are conditioned and phi is a sigma 01 formula, even with parameter in the models, then if the answer is yes, you already force your formula. If the answer is no, then there exists an extension which forces the negation of the formula. Because if the answer is yes, it means that every path through the tree will already satisfy your sigma 01 formula. And if the answer is no, then you take the subtree of nodes which witness the failure, and you will have another computable subtree. And a very small technical lemma from Friedman says that actually, if you have a model of RCA knots, and if you have a set G so that you add just the set G to your model, so you do not close downward under delta 01 comprehension. And if when you add it, you satisfy a sigma 01 induction, then when you close downward the delta 01 comprehension, you are a model of RCA knots. And it's very easy to see. By definition, M bracket G will satisfy delta 01 comprehension because you make it closed under delta 01 comprehension. And all the sets that you add to M bracket G are definable, are delta 01 definable from M union G. And so any sigma 01 formula in this bigger model can be translated into actually a sigma 01 formula in the original model. With a little bit careful about where it positively happens and negatively happens, but it's very easy. So what we can show is, given a condition in this notion of forcing for which a condition is an infinite binary tree, and if you have a sigma 01 formula with parameters in the model, with small x and big X, so that the condition forces the formula to be false for some b. Then there exists an extension which either forces the formula to be false on 0 or forces the formula not to be closed under successor. So here I claim that if this formula if this lemma is true, then you can preserve sigma 01 induction. You can build a path so that the path will satisfy sigma 01 induction. Because this just tells you that if the formula is not true for all the b's, then either it's not true at the start or it's not closed under successor. So still, we have three cases. So given a condition, define the following sigma 01 set. So the set of all x so that the formula holds for x. The first case, 0 does not belong to W. Then, because it's a sigma 01, because it's a forcing question, there exists an extension forcing none of phi of G on 0. Second case, some A belongs to W and A plus 1 does not belong to W. Then, and here we're exploiting not abstractly the fact that you are a forcing question, we are using this particular forcing question. I claim that there exists an extension which forces phi of A G and non-phi of A plus 1 G. Why? Because since A belongs to W, the condition T already forces phi of A G. And since A plus 1 does not belong to W, there exists an extension which forces none of A plus 1 G. But because forcing a property is closed under extension, you still also force A and G. So you simultaneously force the two of them. And in third case, you have 0 which belongs to W, and for every A in W, no, for every A in the model, if it belongs to W, then the successor belongs to W. Then this is not possible because this would witness the fact that you fail sigma 01 induction in the ground model. So here, what we re-exploited is the fact that since the forcing question for Soloway forcing, for Jokic forcing was extremal, you can, if your forcing question answers yes to a sigma 1 formula and no to another sigma 1 formula, you can find a simultaneous answer for both questions. This is what you exploited. And also note that here, any extremality is sufficient. So if you are extremal on the sigma 1 or the pi 1 side, this will still work. Okay. Another application, another example of preservation of a sigma 1 induction is the statement that every set can be made a delta 02 from the viewpoint of RC naught. But I think I'm going to talk about this in the next lecture.